Okay. So we all stand math. So let's do some math. Here we go. Okay, so today we're going to look at product patterns. So think where this is. Let's put this in context, right? We've been talking polynomials. Right? Last time we talked about new stuff. A few days back, we talked about what it is to be a polynomial. We talked about how to add, subtract, and multiply polynomials. Well, today we're going to look at some pretty cool stuff. This is, if you're a math person, this is really cool stuff. So let's click them all the way closed, phones away, earbuds away, all that stuff, please. I want your total attention here. You're going to love this. So we're going to look at some types of products we can take with a specific kind of polynomial. We're talking about a binomial. We're going to look at some binomial product patterns. First of all, let's remind ourselves about something that we've mentioned this year, but we haven't really dealt with it in great detail. So we'll kind of come back to it here. Let's get Chromebooks should all be closed. I want everybody else's attention up here, please. Thank you. So conjugates. What's it mean to be a conjugate? If I've got a binomial, I've got a first term and a second term, right? So if I'm adding those two terms together, like I have something where I've in the form a plus b, where a and b could be whatever. A could be like 3x and b could be 11 or something. Who knows? Then the conjugate of that binomial is going to be the same two terms, but subtracting them instead of adding them. Okay, so in other words, a minus b is the conjugate of a plus b, and a plus b is the conjugate of a minus b. Okay? So what happens when we multiply a conjugate pair together, an a plus b times an a minus b, or vice versa? It makes no difference. I end up getting a squared minus b squared. So we call that a difference of squares. Okay? The product of a conjugate is the difference of the squares of the terms. Okay? So let's look at an example. So what if we had something like, let's say, 2x plus 5 times 2x minus 5. So what's my a and what's my b in that pattern? So you'd include the x. So the a is the 2x, right? So all that stuff is a, 5 is b. So I end up with a plus b times a minus b, and we know that pattern, right? The outcome is just a squared minus b squared. Okay, so we're going to get a squared minus b squared. What's my a again? 2x. And my b? So we just have to simplify that. We're done. So what is, by using our properties of exponents, what is the quantity 2x squared?
4 times x squared.
4 times x squared, because I'm going to square the 2 and square the x, right? So I get 4x squared minus 25. Simple. And so there's one pattern we're going to look at today, the conjugate product pattern. Okay, now we're going to look at some binomial expansion. So what if we've got a binomial to a power? Okay, this can get difficult if you don't know the tricks, right? Like what if we wanted to do a plus b to the fifth? Well, I'll tell you what, just to kind of put this in context, what if we wanted to multiply? I just want to kind of remind you what it means to multiply a bunch of things together. What if I wanted to multiply something like, oh, let's say 2 times 3 times 4 times 5 times 6. Okay, well, how would you do that?
Just 2 times 3.
2 times 3 is 6 times 4 times 5 times 6.
6 times 4, which is 24.
So that's going to be what, 120 times 6, which is 61. Okay. Now those are just numbers, so it's easy, but can you see where that would be kind of tedious if you had binomials that you're trying to multiply out, right? If I wanted to multiply out a plus b to the fifth, remember, that is not as simple as a to the fifth plus b to the fifth. It's a plus b times a plus b times a plus b 5 times, right? So if I wanted to do that problem, I would first have to do that problem, and we know that one. That's going to be a plus b times a plus b is a plus b squared, right? And we know that one. First part squared plus 2 times the product plus second part squared times a plus b, etc., right? 3 others out there, you got to multiply by. Yes, sir.
Why is it in standard? But when we're doing the stuff we just did, well, why is it?
You mean, what do you mean by that? What's that form?
No, why is it in 2a plus 2ab plus b squared? Why is
Well,
it-
because I just multiplied those two out, right?
So you just put it into.
I just did that part in my head, because you guys know that part, right? You know how to do a plus b squared. That's a pattern we've talked about. It's the first term squared plus 2 times the product plus the second term squared, right? Phone should be away, please. Okay, so look what I'd have to do then. I'd have to take that whole big thing times a plus b. Distribute an a all the way through it, distribute a b all the way through it, add up like terms. Get an answer. That's a little bit of work. Then I've got to take that one and I've got to distribute, I've got to multiply by another a plus b. Distribute the a all the way through, distribute the b all the way through, add up like terms. Simplify everything, right? Do it again. It's a lot of work just to get one product, right? Wouldn't it be nice to have a simple way to do this, a shortcut, right? It'd be a lot easier. Say it again.
Is it triangle?
It's Pascal's triangle. Yeah, Pascal's triangle is what's going to save the day for us. It's going to lead the way.
Well, I don't know about that.
No.
Okay.
Get out
So
of
they're
here.
gonna say-
So here's Pascal's triangle. So what Pascal's triangle does lots of stuff, but it does something for us today. Now does that look scary?
It looks like he's trying to explain trickle down economics.
Trickle down economics doesn't work. It's impossible to explain because it doesn't work. That's been shown time and time again. Even though we keep trying it doesn't work. So this is really simple to build, right? Simple to build. Pascal's triangle, the rules to build Pascal's triangle are very simple. When you want to build, you want to move from a row to the row beneath it, all you have to do to populate, we'll call them cells or squares or whatever. I mean, I wouldn't normally write this with squares. You just write the numbers. Okay? Like I would, instead of writing it this way, I would just write it as 1, 1, 1, 1, 2, 1. But either way, the rules are, when you want to come up with a number in a following row, one that's lower than the one above it, you're just going to add up the numbers that are above it, that are immediately above it, right? Well, there's only one number immediately above that 1. It's a 1, so that stays a 1. Same thing there. The slopes of Pascal's triangle, the sides will always just be 1s. They're never going to change because you're only adding up a 1 above it, so they never change. But inside they do. Inside, 1 plus 1 is 2, right? So we get a 2 there. But what am I going to get here? 4. Not 4. I'm only going to add up the 2 above it, so I'm just going to get a 3 and a 3. If I work my way down, this is going to be 4, 6, 4 and 1. Good. And we could keep going.
This is fun.
15, 20,
Do you already know?
15, 16.
Okay, and it's pretty easy to build. I mean, we could go further. You build it pretty quickly, right? But I want you to notice a couple things. So there are a few things here that if you think about this, it's going to improve your understanding of this relationship. Notice that there is symmetry here about the center of the triangle, right? So in other words, if I look at any one of those rows, forwards or backwards, the sequence is the same. Has to be, right? Everybody get that? Okay. So if I take this row, 1, 4, 6, 4, 1, and read it backwards, same thing. 1, 4, 6, 4, 1, right? Okay, so Pascal's triangle does lots of stuff. Now, it does some kind of cool stuff. So one thing it does, just before we move on, just kind of a fun little thing. If we look at our Fibonacci sequence, right? Remember the Fibonacci sequence we looked at the beginning of the year? Fibonacci sequence, you start with the numbers 0 and 1, and all you do to get another number, just add up the two preceding numbers. So 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 8 plus 5 is 13. 13 plus 8 is 21, etc. We keep going, right? That's the Fibonacci sequence. And it's amazing. Those numbers show up everywhere you look. They're just all over the place, right? Say it again.
Rivers.
Rivers,
That
you
one
look
messed
at
me
you look at pine cones, you look at the sunflowers. I mean, it's just no matter if you focus in on anything that has that where you've got you have to have spiral relations. So like if you looked at broccoli under a microscope, you'd see that if you look at broccoli under a microscope, the little buds of broccoli are going to follow the Fibonacci. It just happens everywhere, right? So if you reconfigure Pascal's triangle, so here's what we're going to do to it. If we take Pascal's triangle, we're just going to reconfigure it. So I'm going to drag each of these rows over so that the left side of the triangle is going to be vertical, right? And then the right side is going to be just kind of a longer slope. But we're still going to do it so that we line things up vertically this time. So all the ones would line up vertically. And all of the second numbers would line up vertically. And the third numbers would line up vertically. It would just become that. Okay, so now let's engage our brains a little bit. So what does this Pascal's triangle do for us? Right? We got all these rows in our Pascal's triangle. What are they doing for us? Well, it turns out among the many things that Pascal's triangle does, it's the Fibonacci sequence, it does all kinds of other important sequences in math. They come out of this triangle, which is bizarre. They all come out of this simple little triangle, but they do. But the one that we want to focus on today is just that the numbers in each row are the coefficients that we get when we multiply out binomials to various powers. Okay, so for example, if we assign a row, so let's look at this. We've got the binomial x plus y, simple one, right? So let's just take that to different powers. Like we'll start off going to the 0 power, then the 1 power, then the 2, then the 3, then the 4. Those become the rows in the triangle. So the row 0 is what we get if I take x plus y to the 0. What's anything to the 0? 1. 1. There you go. Simple, right? 1. X plus y to the 1 is just x plus y, right? So the coefficients are 1x plus 1y, okay? X plus y squared. Go down to the next row. X plus y squared is 1x squared plus 2xy plus 1y squared. What do you know? The numbers in each row of Pascal's triangle become the coefficients. X plus 3 cubed is 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. It's so simple. Those are the coefficients. It's got to be a quick question because I got to make hay.
So we also have to move the exponents.
Okay, so that's the other part I'm going to talk about. So the other part of Pascal's triangle is just, okay, what happens to the exponents? Well, if it's row 3, for example, notice that the sums of the powers of x and y or a and b or whatever you're going to call it, whatever we're using, right? In this case, it's x plus y instead of a plus b. The sum of the exponents is always going to be 3, right? So it starts off with all of the exponents shifted towards the first term. So I'm going to get an x cubed, but by the time you get to the end of the row, all the exponential weight has shifted to the other one. So it's all with the y. Each step to the right, or each term in the expansion, the x's are going to drop by 1 and the y's increase by 1, but the sum stays the same that way, right? It still adds up to 3. So the x goes from x cubed to x squared to x to the 1 to x to the 0. The y's go from y to the 0 to y to the first to y to the second to y cubed. It's just that simple, right? Pretty cool. But so Pascal's triangle allows us to take a really big shortcut here. The x plus y to the 5th that would have taken a whole page of paper to do previously, there it is, right? The coefficients come from Pascal's triangle and the exponents in easy pattern, right? Okay, so let's try this a couple times. So what if we want to do something like, well, we know a plus b squared, that's just going to be row 2. Coefficients are 1, 2, 1, right? And we're shifting the weight from the a squared all the way over to the b squared incrementally, right? Okay, so there's our pattern. Well, what do we get when we multiply this one out here? So this is, what's my a and what's my b here?
2x is for a, 10 is for b.
So I get 2x plus 10. squared. So 2x is my a, right? So I'm going to get 2x squared plus 2 times 2x is my a, my b is 10, plus 10 squared. Just simplify. No big deal, right? Okay, what if I have a negative? Let's do a negative one because we're running out of time. We'll kind of speed this up a little bit. Okay, what's my a this time?
10x.
So my a is 10x. What's my b? Negative 1. Okay, and we're going to square that whole thing, right? So I know that if I follow that pattern, I'm going to get a squared plus 2 times a times b plus b squared. Well, a is 10x, b is negative 1, right? So if I simplify that, what is the quantity 10x squared? Okay, I get 10 squared, which is 100, times x squared, good. 2 times 10x is 20x, times negative 1 is negative 20x, and then negative 1 squared is 1. Done. Okay. If I want to do, what about the cubes? Well, if we fill out this next row, it was 1, 3, 3, 1. So there's my 1, 3, 3, 1, right? Let's do something like x minus y. So what's my a? X. And my b is just negative y, isn't it? In this case. And I'm squaring the whole thing, or cubing the whole thing. So I'm just going to follow my pattern, right? Where I've got a is x, b is negative y, and if I simplify that, I'm going to get x cubed. 3 times x squared times negative y is minus 3x squared y. 3 times x times, what's negative y squared?
1.
It's negative 1 squared, which is 1, times y squared, so just y squared, right? So that's going to be plus 3xy squared, and then negative y cubed is going to be negative y times negative y is y squared, times negative y is negative y cubed, right? The moral of the story is if I take a negative quantity, or a negative number or a negative variable to an odd power, I'm always going to get a negative result, right? Okay? All that happened there is I got a negative term there and a negative term there because I had a negative number to an odd power. Otherwise, I get, when I have a negative number to an even power, it's always positive anyway, right? Okay, one more. How about that guy? We're done. I'm going to follow. So you got to remember my pattern here, though, right? What's a plus b cubed? What was that one? 1a cubed plus 3a squared b plus 3ab squared plus, there you go, right? So our a this time is what?
10x.
So 10x and negative 9. Good, so we end up with, here's my template, right? A cubed plus 3a squared b plus 3a b squared plus b cubed. Plug them in. That's a 10x, that's a 10x, that's a 10x, because that's an a cubed, an a squared, and an a. That's a negative 9, negative 9, and a negative 9, right? Following my pattern, just simplify. 10x cubed is what?
1000x cubed.
Yeah, 10 cubed is 1,000, and there's my x cubed. Let's see here, I've got 3 times negative 9 is negative 27, right? 10 squared is 100, so negative 27 times 100 is negative 2700, and then I've got an x squared, right? Because I'm squaring the x. Let's see, here I've got negative 9 squared is what? 81 times 3, that's 243, times 10. I just add a 0, right? And there's my x. And then negative 9 cubed, well, negative 9 times negative 9 is 81, times negative 9 is what? What's that? 729. Okay. That's it. You get the idea?
Yes.
Okay, so, you know, it's pretty easy to build, right?
Please excuse the
There's a
interruption.
limit to how far you want to go with this, because it
You
takes
will ride
time.
the bus Ringo.
Like if you had to
Today you're
expand
gonna
A
ride
plus B
Gemini.
to the
At the same time,
101st,
so
well,
if
you
you
would
ride
want
Ringo,
Pascal
today
structure.
you're gonna ride Gemini.
Then you'd use the binomial
So,
expansion.
seniors, listen up please. On
For
Thursday,
small
April
powers,
18th,
it's always
this
all we
Thursday,
do.
in Warburg
That's
Court,
pretty useful.
during advisory, will be your class picture. So everybody come to Warburg Court during advisory on Thursday for your class picture.
We need to set
Our
up,
announcement for seniors, if you're interested
about
in
trying to
taking
figure out what
graduation, there's a sign-up sheet.
It's